Hello, and thank you for joining us. Today's webinar topic is Improve Your Trace Element Laboratory Efficiency, Accelerate Sample Introduction with an ASXpress Plus System. Our presenter is Dr. Pete Winship, EMEA Sales Manager for Teledyne CETAC. If you have any questions, please feel free to submit them throughout the presentation or email Pete directly, and he will follow up with you after the webinar concludes. This webinar is being recorded and will be available within a few days. Now I'm going to turn it over to our presenter, Dr. Pete Winship.
Well, hello everybody. Thank you for attending today. My name is Pete Winship. I'm the EMEA Sales Manager for Teledyne CETAC Technologies. I'm an analytical chemist by training, and my background is in trace element analysis. Today I'm going to talk about improving efficiency in a trace element laboratory, but particularly with respect to accelerating sample introduction for ICP optical and ICP MS instrumentation. So just a quick agenda for today's webinar. So I want to go into some general requirements of a trace element laboratory. Most of this, if not all, will sound very familiar to you all. Then I want to go into rising costs of laboratory analysis, so particularly with respect to trace element laboratories. So this is something which has become more prominent over recent years, certainly post-COVID. Then I'll go into a typical laboratory workflow for a trace element lab, and then look into sample introduction in that workflow, and then looking at a standard sample introduction to ICP instruments, and then accelerating that introduction, and then go finish it off with some discussion of workflow efficiency. So, general requirements for a trace element laboratory. So these are what we have here, just some of the requirements for an analytical laboratory, and depending on the lab and depending on the kind of work that they're doing, the kind of samples that are being analyzed, some or all of these will be relevant. So starting off with analytical robustness. This is something which is applicable to all trace element labs. So analytical robustness, accuracy and precision of analysis is key to having good quality data that is then reported. So that accuracy and that precision will have to fall within a certain tolerance for that laboratory environment, and that tolerance is going to vary according to the lab that we're working in. Carryover as well, low or no carryover is also an important part of robustness because it plays into accuracy and precision. So we want to make sure that we have next to no carryover, we have thorough washout between samples, so that our subsequent samples are not then affected and we don't have poor accuracy and precision. Time efficiency as well. So sample throughput and data turnaround. This is going to vary again from lab to lab, but in the case of some laboratories, sample throughput is going to be an important thing, and data turnaround is going to be an important thing as well. So for some laboratories, they might receive samples that they then need to report on within 24 to 48 hours. So efficiency of time of analysis is a very important thing for that kind of laboratory as well. And then cost efficiencies as well. Costs are rising, and this is something that we'll get to. So trying to make sure that we get the best quality data for the cost of operating a trace element laboratory as well. Rising costs of laboratory analysis. This is something which has become more and more prominent, and this is the kind of thing that we're having more discussions with customers regarding just how much it costs to run laboratories and the cost of operation per sample. So for a trace element laboratory, one of the key consumables, one of the key areas of cost is the operating gases for your ICP instruments. So primarily the key one here is going to be argon. So argon is required for the duration of the analysis, as well as time to get your instrumentation ready and warmed up, etc. So the operating costs just in argon are one of the key consumables in this laboratory environment. For ICP-MS instruments, you also might have collision or reaction gases. You also might have additional gases, like you might add oxygen to a plasma, to an argon flow, if you've got a high carbon load that's going through your plasma as well. So operating gases for your ICP instrument are a key consumable here. Electricity as well. So there's an electricity demand to run these instruments in conjunction with operating with the gases that you're using. Then in addition to that, you've got your general consumables and reagents. So the reagents used in your preparation of your samples, reagents that might be nitric acid or hydrochloric acid, it might be ammonia, it might be any number of other reagents in addition to your calibration standard stocks that you're using. Then you've got consumables as well. Those might be pipette tips, they might be bottles, there might be a lot of things that are thrown away. So those are all added to this. Laboratory staff is another, as horrible as it sounds, cost of running a trace element laboratory. Making best use of staff time and effort and their expertise, because laboratory staff are typically highly skilled, highly educated people. This again is something else to be considered on operating costs. And then you've got other operating costs as well, of just general laboratory environment, waste disposal, etc. Fume hoods, fume cabinets, etc. All of those kinds of things. So those are the kinds of costs that you're looking at for a trace element laboratory, and those costs are generally going up. With global supply chains in the aftermath of COVID, there have been challenges with a lot of products and consumables that are going into laboratories, and as a result, those have a knock-on effect to costs of running. And you also might have other issues as well. So in the recent years, we've had issues with getting hold of certain reagents. Acetonitrile is a good example of this when you've got production problems going on around the world. So we'll come back to rising costs, and I'll move on to just a typical workflow for a trace element analysis. So we always start with our samples. Samples are delivered to a trace element lab, they're received, but what we want at the end is we want our data. We want good quality analytical data for the analyte elements in the case of trace element analysis that we're interested in. So how do we get from our samples, so our samples A, to our data B? How do we get between the two? So this is where it will all be quite familiar to everybody. So we start with sample reception. Our samples are received at our laboratory. They might be from the laboratory themselves. It might be a research environment. There might be samples that have come in from outside, and they might have come from a particular customer. So, but the samples are received. We might be talking about 10 samples or 20 samples, a relatively low number, or we might be considering a large project where there might be hundreds or even thousands of samples that are on receipt. They then need logging. They need all of the information associated with them, logging on a system. There might be barcoding involved, etc. So those samples are brought in, and then you need an analytical plan. You need a plan of how to analyze these samples. So you need to know as much about the samples as you can. If there is an expected concentration of analytes in these samples, or they might be complete unknowns, but you need a plan as to how to proceed, because you can't move on to the next step without that. So the next step, sample preparation. So what do you do with these samples? So there's, as part of the plan, there will be a process of preparing these, putting them in the correct form or state for them to be introduced into your instrument so you can generate your data. So there will be a means of preparing the samples themselves, but in addition to that, you never just analyze the samples on their own in a trace element lab. There will always be calibration standards that need preparing, blank solutions, there will be QCs that need preparing, all in conjunction with your samples. There might be numerous steps involved in this. So for your samples, there might be digestion required, there might be filtering, you might need, well, you will need to dilute them to one extent or another. There might be spiking of certain reagents or an internal standard. So there's a lot that goes on in this area in sample preparation. Sample preparation is one of those areas that's typically underestimated in the amount of time and effort that goes into it. So the next step, once you've prepared your samples, you need to introduce them. You need to then feed them into your ICP instrument so you can generate your. But again, here's an area where there's a lot more thinking required than you might think there would be. So depending on the sample that you've received and the kind of state that it's in for introduction, in terms of a liquid introduction, which is what we're considering today, there will be a nebulizer and spray chamber arrangement that's sat between your samples and the ICP essentially. So there are various different types of nebulizers. So which nebulizer are we going to use? It might be a standard concentric, it might be something a bit more complicated than that. So the next question, automation. Is there automation involved? Typically there is. If you've only got a handful of samples, there might not be, but typically you will have automation, an autosampler to deliver your samples to your ICP. This is certainly crucial if you've got a large number of samples. So if you've got tens or hundreds or more of samples, then you would typically have some sort of automation. There might be a rapid introduction technique, a rapid introduction system that's associated with this. There might be other considerations as well, temperature control, for example, or something similar. So all of that is considered in the sample introduction step. Once you're through sample introduction, your sample one at a time is then fed into your ICP, delivered to your ICP, where your sample is broken down, it's atomized, it's ionized, or in the case of optical emission, you've got to have photon emission, and you basically detect your analytes, your analyte elements, or your isotopes, and you generate data from it. So you get your data output after your samples pass through the plasma. So your data output is then taken, it's processed into whatever form that you want it to be in, the data is interpreted, and then you do your reporting and generate your conclusions from it. So that's the full workflow. There will be other nuances between these as well, other consideration to factor as you go through that workflow. The key thing here is that there are numerous aspects between your sample receipt and your data that you receive at the end of it. And all of that takes time. There is quite a large amount of time between A and B, start and end of this process. Now that amount of time is going to depend on the kind of samples that you have. So a lot of that's going to factor into the sample preparation side. It's going to be determined by the number of samples you have, the analytes that you're interested in. You only might be interested in, say, 2 or 3 analyte elements. You might be interested in 50 of them. So there's a large number of variables here that will determine the amount of time that it takes between sample receipt and your data at the end of it. So today, I'm going to focus on the sample introduction aspect of this. So how we can look at this as an area to improve efficiency and reduce that time to getting to your data. So typically, sample introduction for most sample types, many samples, it's relatively consistent. So you are typically introducing samples as a liquid, introducing it into an ICP. There'll be some variations, different flow rates, possibly a different nebulizer, but ultimately you're delivering it to your ICP. Now, what I want to discuss today is just to point out just how the standard sample introduction actually can be made far more efficient, be made much faster, and you can reduce your amount of time that you're operating your instrument for per sample. So if I take you back to the rising costs of consumables such as argon, such as your electricity for running your lab, there's time that can be saved here to make the whole process far more efficient. So, sample introduction requirements. So let's look at some just basic sample introduction here first of all. So I've mentioned a lot of this already. So a typical sample introduction apparatus and process includes the following. So certainly the following questions. So you've got your sample. Do you need a particular type of glassware interface for this kind of sample? Do you need a particular nebulizer, for example, or spray chamber? So do you need a particular, say, could you work with a standard concentric nebulizer, something of sort of a moderate flow rate? Or do you need a nebulizer that can handle high TDS, total dissolved solids? So something like a V-groove nebulizer. Or do you need something like an ultrasonic? There's a few questions to answer there. Most analysis is operated with a standard concentric, but there are exceptions to this. Then how many samples do you have in your batch? Is automation required? What's your laboratory environment like? So do you need an enclosure for this? Do you need to enclose your samples to make sure that they're protected from an outside environment? So you might be working in, say, a catalysis lab, for example, where there can be quite a high concentration of acid vapor in the immediate environment, so that has a knock-on effect to your samples and your automation. So is an enclosure required? Good question there. So what I now want to do is I want to compare a standard approach to sample introduction and then look at an accelerated approach, just to show you what kind of efficiencies can be made from the sample introduction process. So first of all, if we start off with what you consider to be a standard approach, so we have automation. So for example, it could be our 2-rack, 4-rack or 8-rack automation. We combine that with, we operate it with a peristaltic pump. Now, typically that's the peristaltic pump which is mounted to your ICP instrument. And then we work with a spray chamber and a nebulizer. So typically something like a concentric nebulizer and say a cyclonic spray chamber. So what you can see here in the diagram on the right-hand side of the screen, so we've got essentially our standard setup. So I mentioned before automation, a peristaltic pump, and our nebulizer here. So basically, we go through this process. So in the case of the automation, the sample probe moves to a sample position or a standard position, or it goes to a blank, but it will go to a certain position, say a sample position in this case. Next, the peristaltic pump turns on. So that's the pump here that's typically on the instrument. And then that will pull sample from the automation and it will follow the arrows of this pathway. And it will ultimately, the sample will be delivered to the nebulizer. Now, that takes a certain amount of time, depending on the length of the tubing that's attached to the peristaltic pump, and also depending on the speed, the revolutions per minute of that peristaltic pump. So when the sample's been delivered to the nebulizer, that's when, typically for standard introduction, the measurement starts. So the measurement process starts. The instrument starts detecting, it starts measuring what's passing through the plasma. When it's finished that process, when it's finished going through its analyte suite, which will take a certain period of time depending on how many analytes there are, how many replicate measurements are need to be taken. When that is complete, the measurement then ends. Now, when the measurement ends, that's that data collected, and then the sample probe goes to the rinse station on the automation. Now, the peristaltic pump is continuing to pull what's coming from the probe through it to the nebulizer. So as the sample probe moves to the rinse station, there's still sample being pushed through the nebulizer. And then after a certain period of time, you'll have rinse solution coming from the rinse station going through to the nebulizer. And that's our washout period. So after a certain amount of time determined in the operating software, the lines between the sample probe and the nebulizer will be washed out, and we'll be back down to baseline and we'll be ready for our next sample. So all of that takes a certain period of time. And that period of time is determined by the tube length, the pump speed, and the analyte sweep that we're measuring at the time. So just to show you this in how it looks in sort of a graphical form. So this is a diagram, a chart that I'm going to be coming back to twice. So for the first time here, we're going to follow the red line. So the red line of this diagram here, this is our standard sample introduction. So we start off, if we look at the baseline here, and we start looking at this, and this is the period that we're pulling the sample through the tubing via the peristaltic pump, and then all of a sudden it gets to the nebulizer and hits the plasma, and we start, that sample signal starts rising, and then we get to our measurement stage. So let's say, for the sake of argument here, after 30 seconds, we're in a position to measure. So we measure our data on the peak here, then the analysis is complete, and the sample probe raises and moves to the rinse station, at which point, when the sample is finished going through and through the nebulizer, and we've got rinse coming behind it, then the signal will come back down to baseline. So let's say, for the sake of argument, we've got a 30-second wash-in time, we do 30 seconds of analysis, and then we go into a washout phase, which might take 20 seconds or more, just as an example. So that's what a standard introduction looks like, just based on introducing our sample via a peristaltic pump. So we'll come back to this shortly. So if that's the standard way of doing it, what can we do to accelerate this? Well, we can go back to what our standard introduction arrangement was. So our automation, our peristaltic pump, and our nebulizer and spray chamber on the instrument. We can add another component. So in this case, we'll add our ASXpress Plus system. So this is what you can see here on the right-hand side of the screen. Now, there's two versions here. There's the white one, which is for aqueous samples, and there's a dark grey one here, and this is for oil samples. But today we're just going to consider the aqueous samples for this today. So we're going to add this component into the mix. So the ASXpress Plus system, this is composed of basically three components. So we have an electronics module, so this is the tall part of it. The tall system, the tall part of the system, this contains our electronics for everything to run the system. Then we have the smaller part here. This is our valve pump module. So the valve pump module is made up of a vacuum pump inside here. And then above that, we've got a 6-port switching valve that's got a sample loop on it as well. And then we have a piece of software that works with ICPs and the automation to make all of this work together. So what you do is you put all this together and you position the valve pump module component of this close to your nebulizer. And all will become clear as we talk through this. So what I now want to go through is, much like I did with the standard approach, I want to go through an accelerated sample introduction. So there's two stages to this. There's what we call a loading stage and an injection stage. So if we look here, this is similar to the diagram that we had before. So we've got our automation here, if you can see my cursor. And then we've got, on the other side, we've got the peristaltic pump as we had before, and the nebulizer. It just so happens in this case they're the other way up. Now, the ASXpress is this aspect in the middle here. So just to talk you through this. So an introduction with the accelerated sample introduction process. So we turn on the peristaltic pump now that, for our ICP, and that continually delivers a carrier solution to the nebulizer and ultimately the ICP. So that might be something like a low concentration of nitric acid, a 1 or 2% solution. So this is represented here by this dashed red and white line. So we've got a carrier solution, it's continually being pumped to our nebulizer. So what we do next is our sample probe moves to a sample position on the automation. Again, or a standard position or a blank or whatever, but let's say a sample position. The next thing that happens is that the vacuum pump on the ASXpress turns on. We very quickly pull our sample from a sample position and we load it onto the sample loop that's on the 6-port valve on the valve pump module of the ASXpress, and it sits there. So that at that point, we consider the loop is then loaded, and that's the end of the first stage. So very quickly, we've taken the sample under the action of that vacuum pump, we've positioned it on that sample loop, and that sample loop is very close to the nebulizer. So we've reduced the amount of time that it takes going through all of that tubing beforehand, and we've got it close to the nebulizer. So the next stage, our injection stage. So what happens next is that 6-port valve on the valve pump module switches position, and it takes the sample, which is the green line, and it puts it into the flow path of the carrier solution, which is the red and white lines. The red and white line, the carrier then pushes the sample out of the sample loop to the nebulizer. So, and because we've positioned that close, that can happen very quickly. So it can be very quickly in the nebulizer. So the sample's delivered to the nebulizer, and at that point the measurement starts. Now, unlike the standard introduction, we don't wait for the measurement to finish before we do other things. So whilst the measurement has started, the sample probe goes to the rinse station and starts washing out the sample probe and the line up to the ASXpress switching valve. So the washout has already started. And all the while, the carrier solution cleans the sample loop behind the sample as it's pushing it to the nebulizer. So by the time the measurement ends on the ICP, we have cleaned and done all of the washout of the sample probe and the sample loop behind it. So the 6-port switching valve then switches back, the loop empties of anything that's in there, and we move on to the next sample. So I've described that, all of those processes that actually happen. Now, this is what it actually looks like in comparison to our standard introduction. So if we now look at the green line with our rapid introduction, and we've started at our baseline signal, and we've rapidly pulled up our sample, switched the valve, excuse me, and the sample is being introduced to the ICP. So all of a sudden, our sample signal goes up, and then we can start our sample measurement much sooner. And then by the time our measurement is complete, because we're not waiting for our sample to pass through, we've emptied our sample loop after the measurement's complete, we then go down to baseline much quicker. So we've taken out the washout phase at the end, we've factored it into, it's operating at the same time as the analysis. So we can get to baseline much, much quicker. Now, depending on the number of analytes that you want to analyze, depending on the size of the sample that you want to go through, we can really cut down the amount of time it takes to wash in, measure, and wash out each sample. So we can really cut down the amount of time it takes per sample for the introduction process. So just to give you an idea, so there's 2 pieces of video footage I wanted to show you. So the first one is just a general introduction, just to show you visually how this actually operates. So what we've got here, before I start this video, we've got on the right-hand side of the screen, we have got our auto sampler. So this is our ASX 560 auto sampler with 4 racks. And you'll just see at the back end of the rack, next to the rinse station, there's a couple of dark blue samples there. Now, over here on the left-hand side, towards the top of the screen, you'll see there's glassware for our ICP, and then under it, we've got our valve pump module for our ASXpress system. So just to show you, I'll just talk you through what's going on. So the system very rapidly pulls up sample onto the sample loop, the valve switches, and then our carrier solution pushes it very quickly off the sample loop and pushes it to the nebulizer. So this can happen incredibly quickly. So you can really cut down the amount of time per sample. So in the meantime, the sample probe goes to the rinse station for its cleaning step. We do complete the measurement, and then the loop empties, and we move on to the next sample after everything's washed out. And that's that. And that can happen incredibly quickly. So just to give you an idea, we've done a comparison between essentially standard introduction and accelerated introduction, so with and without the ASXpress system. So this is the same analysis, the same measurement of the same analyte suite, and the same measurement process. So what you'll see on the right-hand side of the screen, this is just the automation where the sample's being pulled up and introduced to a nebulizer via the peristaltic pump. And then on the left-hand side, we've got the same setup, the same automation, the same racks, and that's connected to our ASXpress. So essentially, we have got some standards at the back, and we've got 60 sample positions, 60 samples in this rack here on both autosamplers. And basically, we're going to go through the same process and just show you how different it can be. So this is just an example. So what you'll see here is the ASXpress system will start really accelerating through these samples, and we've accelerated the time here just to show you what the comparison can be. So we're now up to half an hour, and the Express is so much further along than with our just standard automation. Now our ASXpress approach completes the rack and the standards at the back in 47 minutes for the analyte suite that we're working on. And in the meantime, the standard setup is still going through the samples. So this was just to give you an indication of what kind of time that we can save here. And it really depends, as I mentioned before, on the analyte suite that you're interested in, the sample volume that you need to put through. But we get to the end point of the 60 positions on the sample rack, and we've basically we have saved about 21 minutes by using the ASXpress. Now, the thing to note here, that's 21 minutes of electricity, that's 21 minutes of argon, that's 21 minutes of any other gases that you are adding to this as well. So going back to efficiency. So this is going back to the slide that we had before on rising costs and laboratory analysis. So if we look at this, we can really see where the ASXpress system and accelerating your sample introduction process can save us on the consumables and the costs of trace element laboratory. So basically, if we look at argon and we look at electricity, the two key consumables in our trace element laboratory. So overall, just to conclude, why accelerate the introduction process? Well, if you've got large numbers of samples coming in, if you go through tens and hundreds of samples a day, then this is where you can really accelerate the introduction. You can save a lot of time. That's the key thing here, saving time. And if you save the time of introduction, then as I mentioned already, then we're looking at lower argon usage or other gas usages. And we're also looking at reducing the amount of electricity that's used per sample. Or you could look at this look at it in a slightly different way. So yes, you're saving that argon, you're saving that power, or for the same time period as you might have gone through for a standard introduction, you can analyze more samples in that same time period. So the question is, it comes down to what are you going to do in this case? Are you going to save the time, realize the savings, or are you going to get through more samples in that same time period as you were? So thank you for your attention. I'm going to wrap up there. If you have any questions on rapid introduction, on workflows, etc., please feel free to reach out to me. This is my email address below, or you can contact us via order entry teams or other colleagues of mine at Teledyne CETAC Technologies through our website. Thank you for your time. Thank you.